Good day, students. This is one of my favorite chapters. It's called Graphs That Enlighten and Graphs That Deceive. I just kind of love that terminology because it really talks about what's important in statistics and why we need to kind of pay attention to what we're looking at. And so here is a list of the graphs that enlighten and the graphs and their characteristics that deceive. And so after a few seconds of writing them down, here you go. The graphs that enlighten are the ones with the star in yellow. Those are called dot plots, stem and leaf plots, time series, bar graph, parietal chart, pie chart, and frequency polygons. And the graphs that deceive usually have a non-zero axis and pictographs. Now, just so you know, you could be using pictographs to make a bar chart or a pie chart, and the reason you might be doing that is you can hide or distort information. You might have a non-zero axis on a dot plot. So what happens is these things over here are really a way to distort even a good graph. Now, I would actually add the one we just did as well. A histogram is often a very good graph, and in some sense, it's a form of bar chart. All right, although there are two kinds of bar charts. So let's look at each of these and why they are helpful. So I want to create a dot plot with these president ages again. It's just a good set of data to use to do this. And what I would do to create a dot plot, is I would draw an axis. And a dot plot is like a histogram, but just for single data. And so I would let you know that it's 0 right here. And I'll probably start at age 40 and go to age 50, 60, 70. And then I would keep frequencies 1, 2, 3, 4, 5, 6, 7, 8, etc. And now what I would do to make this dot plot is I would essentially make a dot, and in my case, I don't make a dot, I usually make an X. And so I would go 57, that's 1, 61, there's 1, 57 again, so now I go up to 2, 57 again, up to 3, 58, 57, 61, 54, etc. And what I would end up with is essentially sort of a histogram with a class width of 1 that would, or a bar graph if you wish, and I can just read the data and place it on my chart. I often actually do this with student test scores, like on a final exam, to see if there are any trends. Generally, different trends I look for. One trend I look for is I look for kind of a symmetric trend distribution type look. So the bars will kind of come and give this sort of shape. If that happens, I think the test generally was pretty fair. But if I have a low average, then I might allow students to do corrections. But if the average is, in the C or the B range, then I probably won't do that. But if it's lower, then that just means I probably made the test too hard or I wasn't clear. So I can make a determination off this dot plot. Another thing that'll happen with the dot plot is I might get a shape like this, which is bimodal, and generally that means these students understand the material and did really well, and these students didn't. So then sometimes I'll create corrections on an assignment just for students in this category in order to move their part of the curve up to something like this. They can't be higher than the other people, but they can move up from where they were if they were low. So those are things I do with grades with a dot plot, just by looking at the general shape of the graph. And dot plots give me that idea really quick. Okay? And in fact, the other nice thing about a dot plot, besides the fact that it shows us the shape of the distribution, is that I can go back and I know that this is 54 and I know all four of these are 57. I can actually recreate the data. And for that reason, dot plot's like a 3-star to me. I use it all the time. It's one of my favorite ones. Okay, let's look at the next one. So the next plot that we want to do is called a stem plot, sometimes called a stem and leaf plot. We're going to use the same precedent data. When you make a stem and leaf plot, it's really a table. Okay, so it's a table, and you have what you call the stems, and then you have the leaves. And basically what you do is you split the number into a couple of parts. And so what we see here is that we have the 40 through 45, and then we have 45s through 50s, and then we have 50s through 55s, and 55 through 60s, and then 60s through 65s. So in other words, the stem is like the front half of a number on a histogram class, and then the leaves. So this is like a whole class. So when I go through and I look at the data, so for instance, 57, the 7 would go here. 61, the 1 would go in the first half. 57, 57, a couple more 7s. Then an 8 and a 7. And then a 1 and a 4. 68. 49. 64. And so you can see that how I am making the list. Now, I split these up into 5s because I knew this group, we had lots and lots of 50s, and I wanted to split up the 50 groups and the 60 groups because we had, from previous work with this problem, we had lots and lots of data. So I split it up into the 40 through 44 group, the 45 through 49 group, the 50 through 54, 55 through 59, etc. So, but stems, you could, if you just put the 4 there, it could actually represent the 40 through 49s, okay? Or if you put 2 4s like I did, then it represents the 40 through 44s and the 45 through 49s. It represents 2 groups. And so when you make a stem and leaf plot, you can do that. Now, the nice thing about a stem and leaf is that you have all the original data. And what's super easy with a stem and leaf, and this is why I like it so much, is it becomes super easy to sort. So like this 50 down here, we can see, because it's only the numbers 5 through 9 or 0 through 9 that are listed in the leaf section, it becomes really super easy to put things in order. All right, if you have all the data listed, it's super easy, and then you can put all the data in order. So the nice thing about a stem and leaf plot is you can order them, you can remake the plot and put stuff in order. And you can also reproduce the original data, all right? And it shows you the distribution of data. I know it doesn't sound very interesting, but what you could do
let me get this correct. I'm using the thing incorrectly. Okay. If you do that, I just copy that there, and I turned it sideways, and now it kind of looks like a histogram. If you think about it, look at this. There's a bar, there's a bar, a bar. If you turn your stem and leaf sideways, it kind of looks like a histogram. And so I think that's sort of a nifty sort of part about it. So you can also figure out shape of the distribution when you look at a stem and leaf. Now, can you do a stem and leaf with 3-digit numbers? Well, first of all, 1-digit numbers, yes, the stems would then be 0. 3-digit numbers, you might have a 2-digit stem, so the 110s would have an 11 stem. And so that's pretty much basically all the stuff on a stem and leaf. So let's go to the next one. Generally, on a time series graph, we let people know we tend not to start at 0 because time doesn't start at 0. But we start at a certain point of time. A really popular one I have seen is like the value of the stock market since 1900. All right. And so you'll see it maybe marked off in 10-year increments on the bottom of the graph. And this is time since 1900. So you'll see it labeled in some way like this. And then over here, this will be in number of shares, or cost of shares in Dow, say in the Dow Jones Industrial Average. And so in 1900, the cost of the shares in the Dow was like, maybe $500, right? And then this is 1,000, and then ... Today we're up to almost 45,000 for the cost of the shares. And then what you might see is a graph that is marking things, right? And the Dow's going up, and then you get to 1929 and the Dow crashes. That's the crash. And then it stays steady and it starts to go up again. And you see the Dow, and this can help you see trends over time. Time series graphs show you trends over time. And that's can be very valuable, and so they're very helpful. Sometimes these trends over time are very straightforward, i.e. a lot of the climate change graphs, they tend to look like this, like the temperature's blowing up, but there's a lot of questions about the data they use to put in those. But they try and show you this, like the temperature's going to be way too hot next year, et cetera, et cetera. Anyway, those are things you want to look at. And again, if you have bad data, hence the climate change one, if you have bad data or your data is biased in some way, you can make a correct graph and everything about that graph is true, but the data behind it might not be as true as you would hope. Now, you can somewhat reproduce data from a time series graph. You can grab the time and the value. You can do that sorts of stuff. But in general, you're not going to produce it exactly because sometimes it's hard to tell from a graph if the numbers are exact, but you can produce it approximately. All right, let's look at the next one. So the next category are bar graphs and parietal charts. What's a bar graph? A bar graph is just a situation where you make a chart of categorical data, and then the bars are equal with. And so we've seen lots of bar charts. So you might have something like uh, um, smoking, somebody's a smoker, somebody's a non-smoker, okay? And you would then have a bar chart that would represent frequencies. And the key with those bar charts, the bars don't have to touch, all right? But they will be of equal width. And then the heights will be typically a relative frequency. Although it could be just a regular frequency. So it could be a number. Say you interviewed 100 individuals, and this is, say, 50. So you have 10, 20, 30, 40, 50. And, you had 48 of them say they were smokers, and 52 say they were non-smokers. Or it could be in terms of percentages, and that's why I picked 100. So this would be 50%, and this would say 48% of them were smokers and 52% were non-smokers. Now, that only happens because I picked 100 people, but it could be a relative frequency, and that's a bar graph. What's a parietal chart? Bar graphs are always generally made with qualitative data. All right. If you have numerical data, then you're typically making a histogram, which is essentially a bar chart with a little more information because it's numerical. Because these are categories, we separate the bars, we don't put them next to each other. Now, what's a Pareto chart? A Pareto chart is essentially a bar graph, but when you make the bars for the categories, you put them in order of from largest to smallest. And that's pretty much it. And so Pareto charts will draw attention to categories that have the most in it. And in general, bar graphs and Pareto charts give us a sense of relative sizes, which size is better and which one than the other. Okay? So, next slide. Now, I would say bar charts and pie charts are used often, and they're used, of course, for categorical and qualitative data. And with a pie chart, what happens is you take your groups. So you might have a table, let's say, and that table might have data. So say we were categorizing athletes at Simpson College, and so you might have a football category, you might have the basketball category, baseball, softball. Actually, we could probably put them in the same category because they're, let's call it the baseball softball category. And then we'd have the volleyball, which would include all the beach volleyball stuff, etc. So we'd list all the sports, and then typically we might put, well, the number of athletes in each of those categories. So we're making sort of a frequency table, a categorical frequency table. So football, let's say we had 80 athletes. Basketball, we have two teams, 30 plus a couple of JVs, so maybe 50 athletes. All right. Baseball and softball together, about 25 per team, so 50 athletes. Volleyball, say you have about 12, and you have a men's, so 24, and then you have some beach volleyball, maybe another 10 people, so say 34 athletes, etc. And you could list every sport and list every athlete. Now, we want to make a pie chart of that, and let's say we're just making a pie chart of these four categories. Now, what we do is we want to add these up. So we add this up. This is 4, and then 18 and 3. So we have 214 athletes. So now we have the frequency. So then what we do is we do the relative frequency. All right. And so this will be 80 over 214. And you convert that to percentage, 50 over 214, convert to a percentage. Let me pause and do that. Okay, so now I have the percentages listed there, and those are the relative frequencies. Then what we have to do, if we were going to make a pie chart, we have to convert these relative frequencies to degrees, right? Because a pie chart is a circle. And what's 37.4% of the pie chart? Well, it's going to be 37.4% of the degrees. So what you do is you take 0.374 and you multiply it times 360. And this is something that I don't know, I've seen in the past students have a problem with. But you're trying to convert the percentage to an actual value in the pie chart. And so we multiply those. And now, for instance, I take 0.374 times 360 degrees, and that's approximately 135 degrees. Now I can use a protractor and I can mark that. And so this would be the football category. And then 84 degrees, which is almost 90, so almost looks like a right angle. So these two categories right here are the same size, and this would be basketball, and this would be baseball, and then the last category would be our volleyball category. And that's how you make a pie chart. Now, the nice thing about pie charts is it shows you relative sizes. We can see, oh yeah, football, relatively speaking, is a third larger than any of the other categories. Okay? And therefore we can sort of compare relative sizes of categories. But that's about all we get. In general, pie charts and bar charts should be used only for categorical data. The other ones, the stem and leaf, the dot plot, and the time series, those are used for numerical data, and the histogram, and are very valuable for those. So then you can make a frequency polygon. That's sort of the last quick category is a frequency polygon. And a frequency polygon is essentially like a histogram in disguise. The difference is what you do is when you graph the categories, so say like we had 40 to 50, the president's ages, all right? And say like in the 40s, we knew there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. We knew like there were 3. And so when we made a histogram, we'd make a bar and do that. But what we do with a frequency polygon is instead for the category, over the midpoint of the category, we put like a dot. And then from 50 to 60, say we had 12 presidents. And from 60 to 70, we had 10. And from 70 to 80, we had 5. So let's just think about it that way. Okay? Then the frequency polygon, what you do is you just connect the lines. And so instead of making bars, we're just doing a frequency polygon. And this also gives us the shape of the distribution pretty nicely, and it's a nice way to look at it. Now, if I was doing, if I had to choose, I would almost always choose to make a histogram. But sometimes a frequency polygon's a really quick way to sort of look at something. All right. Okay, let's look at the graphs that deceive. Oh, one more thing about frequency polygons. You could make it relative frequencies, and that's perfectly fine. One more comment about pie charts. The text actually recommends you never use them. Lots of people who are inexperienced with stats, though, tend to use pie charts and bar graphs and stuff like that. And in general, when histograms or dot plots would be much more effective at conveying the information they want to convey. And so I've seen this in my own experience. I worked for a school that was working on accreditation, and the group of teachers did not have a mathematician in the group. There's a bunch of history and special ed. I mean, nice teachers who were really good at what they do. But when they made their graphs of data, it was numerical data, and they made all pie charts. And so they were really hiding good information and bad information within the pie chart, which looked really fancy, but it wastes a lot of effort. So I kind of personally I frown on pie charts. Often there's a better way to illustrate your data. Now, the last thing are graphs that deceive. And so the other thing I used to see with stocks on the news is you would have a graph, and when you looked at the stocks, they would start the axis at like 40,000. All right. And then it'd go to 45,000. And you'd say, oh my gosh, under the Biden administration, or like right after the election, we were up to almost 45,000. And right after the election, what happened? Here's the stocks in October. Okay. And then right after the election, oh, I got it backwards. Here's the stocks in October. They're around 40,000. And right after the election, if you went, week by week or day by day, you could do it however. What happened is, boom, there was a big quick rise in the stocks using a frequency polygon here, or what looks like a big rise. And then there was a little drop off in December, which is actually very typical for stocks. And then now we're back up to Trump, and now Trump's in, and so people are enthusiastic, and it's going up again. And so people look at this and they go, wow, look at how much the stocks have gone up in this short a time. And the problem is we're not starting at zero. If you take this chart and you start it at zero and go to 45,000, then 40,000's up here. And what it looks like is this. And so it doesn't look like such a big change when you start at zero. If your graph doesn't start at zero on the y-axis for your frequencies, then you're purposely deceiving, typically. And that's the issue. You want to make sure that you understand what's going on the vertical axis. And I've already showed you what to do. You can do this if you don't start at zero. And that's because sometimes it's what you're looking at is you're only looking at data from 2020 to 2025. And so you want to let people know that you're not starting at, 0 BC. All right. But on the vertical axis where you're recording frequencies, if your frequencies don't start at 0, that's often meant it creates a deceptive picture. And news organizations do that a lot. Okay? Now, the other thing that is really deceptive is the pictographs, a pictograph. And that's when you use a picture to illustrate something. So, for instance, really easily here, suppose my picture is of a milk carton. So I have a milk carton here, and let me, I'm not sure I can draw milk cartons. It's basically a house. There we go. So I have a milk carton, and maybe this represents the gallons of milk from my dairy farm. Okay, and so I'm using the picture as my bar, and so maybe I produce 10,000 gallons of milk on my dairy farm, and I use the milk carton to represent the picture. Well, suppose I have a very successful dairy farm, and this was say 1980, and now I'm looking at the milk production in 1990, and so what I do is I double the dimensions, right? Because my milk is doubled. So I double the dimensions on my milk carton. All right. The problem is when I double the dimensions, I've only made this twice as big, this twice as big, and this twice as big. But what I've done is I've actually doubled them in 3 dimensions. And if you double in 3 dimensions, you actually make it 8 times more volume. And so even though the volume of my milk was only twice as big, my pictograph makes it look like I improved 8 times. All right? And just look, all I did was just double the lengths, right? Just made them twice as big, and it looks so much bigger. So this often happens in pictographs where dimensions get doubled or tripled, and then you have, if you think of it in terms of volume, the volume is much greater. How do you fix this? Well, you only double the height. So you have a skinny milk carton, right? You double the height. And then now the volume represented is the same. So you have to really watch pictographs. They can be used to lie. Okay? All right. Couple thoughts to conclude. If you have a small data set, typically a table is better instead of a graph. A graph of data should make you focus on the true nature of the data. So you want it to illustrate shape, distribution, and that kind of thing. All right? It should be at least eye-catching but not distracting. All right? That's what pictographs do, is they make it distracting. Don't distort the data. Whatever graph you use shouldn't distort the data. And the ink on the graph should be used for data, not for design. And so a lot of times I'm looking at data and things, and I get really disturbed by lots of color. So too much color becomes distracting. And design features in titles and so forth that it's marketing. And so marketing, let me say this. Marketing has a different purpose, marketing and advertising. its purpose is to catch your eye. And if it's deceptive or not, it doesn't matter. And we see this. I just noticed on Netflix the other day a show that was about marketing, a documentary, and about how companies use the way they package and put products together to essentially deceive. And so all that stuff is meant to not deceive, but to make you purchase. Whereas data is meant to give us information. And so if your graph gives information, that's great. If it becomes distracting and so forth, then you are you could be creating deception without really knowing it. So that's everything in this video. We'll talk to you later and we'll look at these later. Okay? Bye.